Well, welcome everyone to the ACM seminar. Today we've got Ricardo Barros, who's currently at Loughborough University. Ricardo started out his academic life in Portugal, and he's done a kind of world tour, including in Ireland, in Limerick, and also in the States. And yeah, this is his first position in the UK. We've been now at Loughborough for about 6 years, isn't it? So yeah, we're going to hear about these internal wave theories for water waves, but in this three-layer approximation. So over to you, Ricardo.
Thank you, Thomas. I would like to thank Thomas and Osama for the kind invitation. It's my first time here in this part of the country, so good to be here. So as Thomas has said, I will talk about internal solitary waves in an idealized situation where the ocean can be described by a three-layer flow. Okay. So for those of you who have never heard about internal waves before, okay. So these are waves that are not basically at the free surface, okay, in the ocean, but they are underneath, okay. So sometimes what you have is that you have the ocean, for example, especially in the summer periods, a warmer layer of water over a cooler layer of water, okay. Of course, this is also saltier and this is less salted, okay. So there's a natural gradient that promotes this interface, okay. And with the tides and other aspects, you can actually have these huge deformations of the interface, okay? So these wave amplitudes can exceed 100 meters, okay? So just to keep here things in proportion, okay? So you have here the gherkin, which is 179. The current highest wave, internal wave registered, it actually surpasses the 200 meters, okay? So it's a big beast, okay? And it's a very long wave, okay, up to kilometers, and they usually propagate in slow motion, okay, orders of meters per second, okay. So, of course, these things were known since the time of the Vikings, where you had, for example, the entrance of the fjords and the ocean, where you had the version of an interfacial waves being created by the ships, in which case the ships can actually not move, because all the energy that they were using to move was actually used to produce waves, okay? So they call these the dead water phenomenon. But I mean, these are more energetic versions of that same phenomenon. Okay, so these waves can be detected, okay, from space, and using what people call the satellite aperture radar images, okay? So what they see is that these kind of short waves deformations of the free surface, which are always accompanying these big deformations of the interface, can be tracked down, okay, and you can see where these things are. So, for example, here this is the Strait of Gibraltar, and this is the Mediterranean, and you see here clearly a train of undular pore or something like that, and so these will be, for example, the leading wave, and then other waves on the back. And here, even in the Red Sea, you see these wrinkles here, which are a sign or a signature of an internal wave propagating inwards. Yes?
What's the length scale that we're looking at?
Kilometers, I don't know what to say. I mean, this is the Strait of Gibraltar, right?
Okay, yeah.
So it's quite large features. Anyway, so these have been detected. I mean, currently they are known to be in most coastal regions in the oceans. Okay, so in this atlas prepared by the Office of Naval Research, whenever you see a red dot, this is what we call an internal wave hotspot. Okay, so there are plenty around the world. Of course, in the south of China is one of the most sought places for internal waves, because I mean, there's a lot of activity going on. People want to monitor what's going on, okay, in there. Of course, for example, here you also have in the Azores, okay, these archipelago, because it's again, you need to be close to a coastal region to have these, because of the way they are generated, okay, usually with tides, okay. So there's some kind of resonance phenomenon which can be used to actually generate these nonlinear features, okay? So they are important. They can mix nutrients. They are responsible for the mixing of the oceans. And I mean, they have large impact, for example, on submerged structures, like, for example, oil rigs as well. And I mean, they are a nice thing to study. And the majority of internal solitary waves are what we call of the first baroclinic mode. Okay, so typically if your density stratification is continuous, you will have infinitely many modes of propagation. Okay, but typically, actually, 90% of all energy is concentrated on the two first modes. Okay, and the first mode is extensively studied. Okay, and can be actively described by a strongly nonlinear two-layer model, provided that the transition layer is sharp enough. Okay, so what you have here, for example, is a transition between a colder layer of water over a much warmer. Okay, and this yellow line is what we would call the thermal line, which is separating the two bodies of water. And clearly, you see a very broadened feature. Okay, much more broadened than the typical square profile of the KDB, which is there in dashed line. Okay, and the idea is that if you really want to describe large amplitude waves, okay, this kind of weakly nonlinear description should be abandoned, and you should take into account more strongly nonlinear aspects. Okay, so and perhaps the most perhaps the most well-known model in this category of models is what we call the Miyata-Choi-Camassa model. And it has been very successful in describing large amplitude solitary waves, both observed in laboratory experiments, but also for the solutions of weather, okay? Steady solutions, of course. So as far as steady problem goes, this is really a remarkable tool. And for that, the only thing you have to deal with, so for example, we can start with the simplest setting, supporting these kind of waves, which is two immiscible fluids confined between two rigid walls. Okay, so basically you put two homogeneous fluids with constant density ρ1, ρ2. So this ρ2 is greater than ρ1. So we are assuming a stable stratification. And then we put gravity. In this case, for example, it's a long wave model. So for example, we consider that both layers, the thickness of each layer in rest is comparable. We assume that amplitude, over the total depth, for example, is order 1. So it's not a weakly nonlinear model, okay? And well, there's some consideration here on the leading order of the horizontal velocities independent of the vertical coordinate c, or that. And with those assumptions, okay, long wave assumption as well. So which means that we have things, which are much longer, okay, because these are order of kilometers. So we are interested in a long wave phenomenon. Then with this, we can write an asymptotic model based on the other equations, okay, for which this first equation is the conservation of mass and it's exact, okay, but the momentum equation has an order of epsilon to the 4th, okay. So this is how the model is written. It's written in terms of depth average velocities, okay. So we lose one dimension, right? So instead of x and z, we are actually looking only in x and t, okay. So what you have here, for example, this is the thickness of each layer, okay, at the eyes. I's bars are the horizontal velocity depth average, okay. And basically, all the dispersive terms are accounted here in the right-hand side by the introduction of these GIs, okay. So if you drop that right-hand side and set it to 0, this is what we call the shallow water equations, okay, which are hyperbolic, but some of you know. And so this is what I said. So the model is able to retain, particularly well the features of the large amplitude waves. For example, this is compared to Euler solutions, okay, but also with laboratory experiments, okay. So this is a laboratory experiments done by Grew and all. And what you can see is that the profile is fairly well captured up to very large waves, in which case, it's not clear if we should blame the model itself a priori or not, because, first of all, when you have large waves, there's also some kind of shear instability, which is, it starts shedding from the crest, and then it starts rolling up and sheds away. Okay, so part of this could be noise, but anyway, it is what it is. So, but we are very comfortable with this model describing large amplitude waves. And the beauty of it is that mathematically it's a very simple tool, okay? So for example, that PDE system, when we are looking for steady waves, then you find out that the interface displacement is this zeta in a reference frame moving with a wave speed c, then is given by this Hamiltonian system. Okay. So this is a Hamiltonian system with 1 degree of freedom. Okay. So you see that here, basically, you have what? You have, so this is quadratic. So you have a cubic, no, a quartic, actually, over a linear. Okay. So for example, if you would be using the KdV theory to describe this, you will have a potential which will be a cubic. Okay. So this is slightly different. It's a quartic over a linear. Okay. And what we see is that internal waves tend to broaden as their amplitude increases, as we see here, and as you saw in that measurements from the ocean with a yellow line, and that corresponds to the case where you actually do not only have a homoclinic orbit, but actually you can have a heteroclinic orbit. Okay, so this is what happens when you are broadening your wave. Okay, and then suddenly. So this is the limit amplitude, okay? So you can actually connect this trivial state to that trivial state by this continuous connection.
Sorry, what are the axes?
This is x, so x minus ct, okay? And this is just the vertical axis, okay? So I'm looking at, something centered at your. So these waves are all symmetric, of course. Okay, this is a Hamiltonian system with 1 degree of freedom. And the maximum amplitude, which is given here on this purple line, is given by this expression, okay? And it's attained at this particular speed, okay? That's what you can tell. So the limiting solution is a heteroclinic orbit connecting the two equilibria, which is the zero and the amplitude, the maximum amplitude, okay? Now, what is particularly good is that these are what people call the conjugate states, okay? So you can retrieve this zero and this maximum amplitude by looking at those uniform flows which conserve all 3 physical laws of mass, momentum, and energy. So these are exactly the same that you obtain for Euler, okay? So the only difference is that Euler, perhaps the details in which you can connect these 2 states will be different, okay? But at least the same conjugate states are there. Okay, which is already quite remarkable. So you can see this in this diagram where, for example, this is what we call the front curve, which is the speed at which you attain the maximum speed for the existence of solitary waves. For speeds larger than these ones, there are no solitary waves, okay? And here, what you see in this dashed line is the linear long wave speeds, okay? And the solutions can only exist from the dash to the front curve, okay? So in this region, waves can exist and they are of depression, like in that picture. But in this scenario, when they are on this side, they are actually of elevation, okay? So you will have a wave like this, okay? So you have 2 different polarities. And a particular point here, when these 2 curves are tangent, okay, around 0.5, this corresponds to the case when you don't have solutions, okay? It's what we call criticality, okay? And and on top of that, not only you can predict that there are no solutions for this model, there are no solutions for Euler as well, okay? Which has been known for the weakly nonlinear theory, KdV, for a long time. Okay, but although the model tells you that you always have this kind of front connecting the 2 states, it doesn't have to be the same as a limiting wave for Euler solutions, okay? In order to reach the solutions, you have these overhanging solutions or overhanging waves that have been found by a number of authors. And a recent paper by Guan and Paul have described some remarkable solutions like this kind of mushrooms here. It's almost Dutch. But anyway, these are beyond the model. Okay, the model cannot do that. Okay, because the model will always give you a graph, right? So cannot capture these things.
Are these physically realizable? Have these been seen in experiment?
No, of course not. But I mean, this is a numerical solution for steady Euler solution, steady Euler equations, right? I mean, if they are stable or not, I will guess no. But I mean, mathematically they are there. Anyway, so this was about mode 1, okay? And what I would like to focus here now is on mode 2. Okay, so these are the what we call the second baroclinic mode, okay? And so to capture first baroclinic mode, you need at least 2 layers. to capture second baroclinic modes, if you want to use a layered model, you need at least 3 layers, okay? That's what we need. And here, this is an experiment made by Magna Carr. So here you have 1, 2, 3 layers, okay? And you see these bulges traveling around. And these are what we call the second baroclinic mode waves, okay? So the first baroclinic mode wave, for example, all the ideal pigments have to be oriented in the same, or pointing to the same direction, pointing downwards or upwards. Here they can have, I mean, pointing upwards and pointing downwards, okay? So they are different features, okay? Anyway, so these are slower waves, okay? But they are equally important in terms of the global mixing and the vertical fluxes of heat and nutrients in the water column. Okay, now, mode 2, I mean, mathematically, they are much more subtle thing to analyze, okay? First of all, while mode 1 internal waves have been established for a fairly general class of density, continuous density stratifications, mode 2, no, you cannot do that, okay? So you can only do that in a very idealized situation, okay, which requires a lot of symmetry. In that case, you can actually build this solution. Typically, this is what was proven by Tung et al. In 1982, and since then, we haven't done much better, okay? So, but as a consequence of that, you have that most of experiments are actually done in those idealized situations for which people knew solutions were there, okay? The problem is that in the ocean, I mean, those idealized symmetric configurations won't be there, right? So how to deal with this, right? So these are unlikely to occur in the field where most observations are made. And then the question is when symmetry is broken, and it could be by geometry, by assuming that, for example, the top layer is actually much thinner than the lower one and things like that. You could create this break of symmetry by density stratification or non-Business effects. So asserting whether or not these waves exist is actually not a trivial matter, okay? And this is what we would like to try to understand. The first complication that you immediately see when you are describing the study solutions in these non-idealized symmetric conditions is that the solutions, this is a mode 2 wave, which is accompanied by these oscillatory tails, okay? And actually, this famous paper by Achilles and Grimshaw, they have proved that this is a prevalent thing, okay? So every time you have this kind of scenario, and this is motivated by a resonance between the, so when we look at the dispersion relation, you will know that there are 2 modes of propagation, okay? And every time you have a second a wave in the second baroclinic mode, it is actually resonating with a shorter mode 1 wave, okay? And so you have these kind of solutions which can be identified as mode 1 waves, okay, almost linear, okay, blended into the main pulse of the wave, okay? The question is whether or not these tails can be actually suppressed at all, okay? So we'll start from this premise that, I have the hope that perhaps I can kill those ripples, okay, and see whether or not I can make any progress, okay? But the other thing I like very much in this figure is that when I look at this, I see a wave traveling to the left, okay? So you can see here the profile, okay, something like this. And here I recognize this as being the oscillatory tail, okay? But what is interesting to me in this figure is that it seems that there's a hump here, while here, for example, I could have actually 3, right? Is this noise? Is this some feature which is part of the solution? This is something that I would like to see, okay? Okay, so again, we start with this sketch. So a 3-layer flow. So you have immiscible fluids with constant density for rho 1, rho 2, rho 3. I have here some notation. So zeta 1 and zeta 2 will be the deformations for these 2 interfaces. Okay, and I will consider 2 rigid leads, okay, 2 rigid walls. Okay, so long wave approximation will be imposed, weak horizontal vorticity, and stable density stratification, which means this is heavier than that, and this is heavier than that. Okay, And what we do is a generalization of that MCC model to account for 3 layers. And this is now the PDE model. Again, this will be a non-dispersive system if I kill this right-hand side, set it to 0, okay? And if I want to introduce all the dispersion effects, then I have to include these, okay? So I don't want to go much into this. There's another technicality, which is, you see here PI, okay, which is a pressure at a given interface, but you can always play with things and put, for example, the pressure at the top or a pressure at the bottom by using a recursion formula, okay? So let's start with first things first. So linear dispersion relation. We look at this. So we linearize about the 0 equilibrium, okay, for zeta1 and zeta2. And then we use normal modes to write down dispersion relation, which is a big quadratic, okay? And a good thing is that all the roots are real, okay, regardless of the parameters that you put there, okay? So this is very, very good. So there are 2 modes of propagation, which can be plotted here, okay? So this is the faster mode, and this is the slower mode, okay? So this is compared with Euler, so you will see some discrepancies. I believe Euler is the dashed line, yeah, and this is the model in blue. So for long waves, the agreement is remarkably good. Of course, here not so good, right? But this is expected from asymptotics, okay? So what we have here, sometimes, okay, I will set up the certification written in terms of these expressions. So rho 1, that's at the top, is rho naught 1 minus delta 1. Rho 2 will be my reference density, and then rho 3 is that reference density times 1 plus delta 2, okay? And this is used in the oceanographic community where they actually put delta 1 as a multiple of this delta 2, and I will consider this delta instead, okay? So this is just because it's used in the oceanography. And then, yeah, the good thing is that the linear long wave speeds are solutions of this quartic equation, okay? I can rewrite that in this way, okay? And this is particularly useful because when I write something like that, it means that if I define one of them as being gamma, then this has to be gamma minus 1, right? And this will show in the expressions for the weakly nonlinear models, okay? You'll see how. So the KdV appears when you look for weakly nonlinear waves, okay? So here what you have, I've written this for the interface displacement of the upper interface, okay? So it's at the 1. So this is the typical KdV, where you have these quadratic nonlinear coefficients written here and the dispersive term here, okay? So what you see here, where you see gamma written here, is exactly that gamma that I have brought from here. Okay, this is that guy. Okay, where C naught should be replaced by C naught plus or minus, depending on the mode you are interested in. Okay, so you have a KdV. Moreover, if I want to recover the deformation of the second interface displacement, I just have to multiply the first by that gamma. Okay, and I get that proportionality constant. And then what you say is that the first and second baroclinic modes, yeah, this is what I said. So in the expression of gamma, if you replace C naught by C naught plus, you get the first baroclinic mode waves. If you put C naught minus, you get the second baroclinic waves, okay? What you find is that mode 1 always have the same polarity, okay? And mode 2, opposite polarity. So they could be these kind of bulge waves, okay? Or something like this, okay? Convex, okay? Concave, okay? So, and the wave is of elevation for zeta1 if this guy is positive or negative, okay? And of course, in the case when this vanishes, okay, then you don't have solitary waves, and this corresponds to the critical optical condition, which is defined there, okay? So this allows us to represent in terms of the parameter region. So for example, what I have here is the top layer over the total depth, intermediate layer over the total depth, okay? So this is my admissible regime, okay? And then what I find out is that, for example, here in this shaded region, I have the quadratic nonlinearity coefficient for the KdV being positive, which means a wave of elevation, okay? And it means that, for example, if you are above this, okay, which means the intermediate layer is thick enough, you can only expect waves of depression. For example, this is what we take from these drawings. Okay, so this is for the second baroclinic mode. This is for the first baroclinic mode, where the behavior is actually much more subtle. Okay, here it's always the same picture. Basically, here no, there's some kind of bifurcation here. Okay. Okay, so we have covered the linear dispersion relation, or linear theory, weakly nonlinear theory, and then this is the strongly nonlinear theory. Okay, so this is me taking that PD model proposed by Miyata-Choi-Camassa, extending to 3 layers, and then plugging in the ansatz of the traveling wave solution. Okay, so when we do that, you recover a dynamical system. Okay, so this is a coupled system of second-order ODEs. Okay. So you see Z1 double prime, Z2 double prime, and so on. And what is interesting about this system is that I can see the right-hand side of this as being the minus partial derivative with respect to Z1, and that being the minus partial derivative with respect to Z2 of a certain potential. Okay? Which means that these equations, this coupled system of ODEs, is actually the Euler-Lagrange equations for a given Lagrangian, which is written here. Okay, so this is the potential, and this is basically the kinetic energy. Okay, so this is equivalent to a Hamiltonian system with 2 degrees of freedom. Okay. Moreover, depending on the speed, c is always a parameter, right? And depending on the speed, it will have different signatures, okay, for your eigenvalues. So, for example, for the first baroclinic mode, which is waves which are traveling at higher speeds than C0 plus, then, for example, in terms of signatures of the eigenvalues, for example, you have 4 real eigenvalues, 2 positive, 2 negative. And in terms of the surface of the potential, you have a maximum of the surface of the potential. Here, in the second baroclinic mode, which we are now focusing, you have here 2 real eigenvalues, a positive and a negative, and purely imaginary, okay, complex conjugate. And this is a saddle. And here, there are simply no solitary waves, okay, only periodic orbits. Okay. So we are interested in this situation, saddle central equilibrium, okay. And as we know, the dynamics can be very, very rich, okay. Before we do anything with the system, I would like to start by looking at a few asymptotic limits, okay, which can be easily treated. And for example, if I say that you have a small density contrast between 2 adjacent layers, so we have 3 layers, okay, but if I assume that 2 of them are very, very, very close in densities, okay, then what you get is that asymptotically, at leading order, you get that, for example, the one of the interface will be just a flat surface, okay. And the other is just the solutions of the well-known MCC solutions, okay? Well, in this case, it's under Luceni's approximation because of this, okay? So this is one of the features, and then we can actually go back to the model, okay, the fully coupled system of ODEs, and actually retrieve this, okay? For example, this is me setting up the ratio between the top layers 0.9 and the ratio between the 2 lower layers 2. Okay, so there's a big jump here. And what you can see here is that I give a certain speed, I get this wave, okay, almost flat, as you can see, which is predicted by the asymptotics. And then I increase my wave, and I increase my wave speed, okay, and I see that it starts broadening here, and this is fairly flat still, right? So it kind of says that the asymptotics are doing a nice job, okay? What other solutions can we have? For example, this is the case when you have a small density increment across all 3 layers, plus nearly horizontal symmetry of the domain. So this is basically me going back to that extremely idealized situation where you have a lot of symmetry, for which mode 2 internal solitary waves are known, okay, analytically for Euler. And this is me going there and see that, yeah, asymptotically I can see that, right? And these are my predictions, okay? So for mode 2 waves, I have, for example, small to larger and to very large, or waves of, for example, so these are the bulges, right? The convex, and these are the concave, okay, waves. So, and then again, I go back to the coupled system of all these, and I try to replicate these. Okay, and in this case, when you have this polarity, I can easily increase my C, and I see that there's a broadening, and so far so good. But for example, for this case, okay, when I have a thinner intermediate layer, this is as far as I could go. Okay, so I cannot go much farther than that. Okay, keeping one pulse over one pulse. Okay. And I didn't know exactly why, but I mean, something needed to be looked at. Okay. So the other case is, okay, so I presented two asymptotic limits in which I can do something, okay? But are there any others? And another is when, for example, you have a very thin intermediate layer, okay? Then, I mean, here I'm assuming a constant density increment across the layers, but I don't have to do that. It's just for simplicity, okay? What is important really is that the intermediate layer is very, very thin, okay? And in that case, what you have, okay? So here, what you have is that the asymptotic solutions at leading order amount to considerable sense case under the assumptions that the reduced gravities are the same, and the intermediate layer just collapses to zero, okay? And what you get is that in terms of dynamical systems, these decouple almost entirely, okay? So you have these, zeta1 minus zeta2 squared times something that only depends on zeta1, and zeta1 minus zeta2 squared times times something that only depends on zeta2, okay? So you have basically this is equal that, or you have a decoupled system of all these to satisfy, okay? Now, if I start from the origin, when I look at this, any of these, okay, I no longer have solitary waves, but I can construct periodic waves, okay? So I can do that. So I can build periodic orbits starting from rest at 0, and provided that my wave speed is below this threshold, okay? I can do the same for the other, and I can prove, yeah, I can have solutions provided I have that, okay? But I'm only building periodic orbits, okay? Now the idea is that basically, if I try to match, for example, let me see, I'm looking at two periodic orbits, okay? And then I look at that and I ask, okay, when can I say that I have a multiple, this period being a multiple of the other one, okay? And this is the condition that I have to satisfy. And I don't want to get into details, okay? But this can be obtained, and which can be plotted, okay, right away once you plug in the parameters. So for example, here I plug in the parameters. So H3 over H1 is 0.2, okay? Or for example, H3 over H1 is 1.1. And you have very different behaviors, okay? So this is the range of values of n that I can have. And then the idea is that I'm doing basically this. So you have basically this, okay? So suppose you have something like this, okay? And I have another one going like this. If the periods match somewhere, okay, maybe I can build an orbit from here to there, okay? And this will correspond, for example, with a wave of 2 pulses over whatever pulse. Actually, this is not well drawn. This is not like this. This is more like this. It starts from 0 like this. It has to be smooth. So I have one for zeta1, and then I have another one for zeta2. Something like this. So if he happens to touch here, then I could have a wave of 2 humps over 3 humps, okay? And then I only have to do is glue this thing to infinity. So this, instead of a proper wave, is a compact one, okay? Now it has compact support. In the weak sense, we can do this, okay? We have enough regularity to do so. And then I can actually say that, okay, so if you want a wave, for example, with 1 hump, I have to have n equals 1. I go there. It only exists for this value of speed, okay, which is fairly large, okay? And here in this case, for example, it's already here. But most generally, you don't expect to have only 1 hump over 1 hump, okay? There are many more rich families of solutions, okay? So every time you have n being p over q, this corresponds to a wave with q humps for the upper interface and p humps for the lower interface, okay? So we have a way of building these solutions, okay? 1/1, 1/2, 1/3, and so on. Okay. Now, this is a very weird limit, right? I mean, this is collapsing the intermediate layer completely, right? Do these solutions actually exist when you have a finite thickness? Although it's thin, it's finite, right? So this is the thing that we were able to do, right? Can you tell me in terms of time how we are doing?
Sorry. Yeah, 15 minutes.
Okay, thank you. So we were able to do a continuation, okay, from a smaller interface or a thinner interface to open up slightly, okay. So we could do this, and I mean, these are remarkably close to this kind of solution that Magda Carr has seen in her lab, okay. And but the problem is that in the lab, she has never tried to find solutions which are more exotic. Okay, she never looked for 1/2 humps and things like that. But there are actually evidence of those in a different paper. I will just show it to you. So this is a case of an exotic solution. Okay, so here what we have is two solutions, one with a thinner interface, then slightly larger. Okay, and the way we do this has to be very, very finely tuned, because when you just open slightly, immediately you see all these radiating oscillator non-decaying tails, okay? But you have to tune things in such a way that you actually can make it vanish, okay? So if you are not careful at all, when you do this continuation, immediately you fall into a generalized solitary wave, and then you have to tune things in a way to actually get rid of these oscillations, okay? So these are the only experimental evidence that I know from these kind of exotic solutions. Okay, so this is the case of 1 hump over 2 humps, and these were obtained by Gabilov and Lyapidevsky in 2013. So this is a paper written in Russian. I don't know how to read in Russian, but I know how to look at the pictures. So I took it from there. But they never explained properly what this was. Okay. But I mean, the good thing is that these look stable in a lab. They can make it run, okay, and they keep their shapes, and it's a good evidence for us, right? So these unusual features that could never be predicted by, for example, KDV or modified KDV or Gardner or whatever it is, are here, okay, and people know about this. So this is another exotic solution. Doesn't matter. Now, another thing that we could do using this model, okay, is the following. So I'm using the case of boostiness approximation, which, I mean, simplifies the system. And I will look at that particularly idealized situation where you have a lot of symmetry, okay? So I'm considering that the top and bottom layer have the same thickness in rest, okay? And then when you do when you look at the dynamical system under the boostiness approximation, you realize that you have a following property, which is if zeta1, zeta2 is a solution, then minus zeta2 minus zeta1 will also be a solution, okay? So, for example, KDV predicts the non-existence of non-trivial solutions in mode 1, okay? Because you reach what we call criticality, okay? So in the KDV, the quadratic nonlinear coefficient vanishes, okay? So there are no solutions according to KDV. If you want to modify KDV, then actually there will be two solutions, okay? Or Gardner, if you want to call it like that in this case. But using our model, so if you use the Gardner or modified KDV, you will see probably something close to these two solutions. So this is only one, and if I want the other one, I just flip them using this relation, okay? So I flip this, and I say minus zeta2 minus zeta1 is also a solution. But what the Gardner cannot do is this, okay? I still have one solution like this coming from mode. So in this case, I mean, you cannot see very well, but these are typical from mode 1 in the sense that the deformation of the interfaces are aligned, okay? So this is of depression, this is of depression as well. When you do minus zeta2 minus zeta1, both of them will be of elevation, okay? So this is characteristic of the first baroclinic mode. But here, this one, at the same speed, same parameters, same speed, I can have another one. And this one has the features of a second baroclinic mode, in the sense that One points downwards, the other points upwards, okay? These cannot be captured by any weakly nonlinear model because they usually decouple the modes, okay? Here they are not decoupled, okay? And what I see indeed is that if the intermediate layer is thick enough, so 6 times higher than the top layer, what you get is that so this is the amplitude and this is the speed, okay? So you see that this family of solutions, okay, which is coming from the second baroclinic mode, is actually intruding into the mode 1, okay? The mode 1 starts here, right? So all these waves above these are of these characteristics, okay? But they are traveling much faster than they should. Okay, they intrude into the mode 1, okay? Which is quite remarkable, right? So clearly there is a lot of non-unity here, okay? And these are some recent advances that we have made since then. So first of all, we looked at the conjugate states in this 3-layer configuration. So similar to the Miyata-Choi-Camassa model, where the conjugate states can be preserved by using the strong nonlinear theory, the same happens here for the 3-layer case, okay? And as I said before, the 2 uniform flows are said to be conjugate if all the 3 basic physical conservation laws of mass, momentum, and energy hold, okay? So basically, you have to find these trivial states and then hope that there is a connection. It doesn't mean there is, but maybe there isn't, okay? So in terms of the model itself, okay, this is, so these are obtained from Euler, okay, by Lamb, Rousseau, Grew, and other authors. And what we see in terms of our model is that this corresponds exactly to v equals 0 and partial derivatives of v are 0, okay? So what we are talking about is that the conjugate states can be thought for our model as the critical points of the potential, which have the 0 level energy. That's it, right? So the question is, do heteroclinic orbits exist or not? That's a different story, right? But this is particularly good, okay, because it means that at least you have a shot of trying to describe very large waves, okay? And moreover, not only that, but if the model really has, or the solutions have the feature of broadening, then you could actually expect that the longer the waves are, the better the model will behave, because it's a long wave model, right? So this gives us some reassurance to use a model for large amplitude waves, okay? So this is, this is a bit of too much information, but what we have here is the conjugate states, okay? And so what you see on the the blue line is the conjugate states for the first baroclinic mode. These dashed or dotted lines are the linear long wave speeds. Okay, so this is the linear long wave speed for the mode 2. This is mode 1. Okay, and red are the conjugate states for the second baroclinic mode. Okay, so let's see what we can see here. So first of all, for example, you could expect that, for example, if so this is H2 scaled by the total depth, okay? So if the intermediate layer has a thickness which is lower than this value, okay, you should expect, for example, one conjugate flow, one conjugate state, okay, for first baroclinic wave, which probably corresponds to unicity of solutions, okay? Probably there's just a front there. But for example, if you are in this region now you have 2, okay? In the second baroclinic mode, okay, sometimes you have 1, sometimes you have 2 more, okay? For very thin interfaces here. Intermediate layers, okay? And this is just another depiction here, which says that so some lines are full and some lines are in dashed, okay? And the reason we have done that is that because if it is dashed, then it is a saddle of the surface of the potential. Otherwise, it is a maximum, okay? So what we know is that in computing trajectories, okay, it will be much easier to connect, for example, a saddle to a maximum than a saddle to another saddle, okay? And this, at least in the parameter region that we'll use, will give us an idea that, for example, connecting these things, these lines, okay, in full, which is meaning connecting a saddle to a maximum, will be much more likely than connecting, for example, a saddle to a saddle. Okay, so this is basically the idea that we have used, and this is exploring the situation where, for example, so this is the idealized symmetric configuration where you use Boussinesq approximation and whatnot. So we have realized that, for example, there is no solutions for the first baroclinic mode if the intermediate layer is thin enough, but then there are actually two, okay, and they are using the symmetry properties there. Okay, and here we have the second baroclinic mode with this guy. Actually, it's above the solid line is actually above the dashed line. Okay, so here, for example, we expect to have connections to this conjugate state, but perhaps not to that one. Okay, and as you leave here, you see that the dashed line from the second baroclinic mode actually escapes the linear spectrum, right? So here we are already above the first baroclinic mode, and we have done the study to know when this happens, okay, in terms of the parameter region, and this is what we could figure out, okay? So in order to have that, you always need your intermediate layer to be thick enough, okay? And this is how it goes, okay? So this is precisely the case where you have, what, 0.75, I believe, yeah. And so everything is higher than this, okay? And here it means that you have solutions that are no longer embedded, okay? And they can travel at the same speed as mode 1 waves, okay?
You should probably take questions.
Yeah, okay. Okay, so this is the aligning again the discussion that I have made with connecting a maximum, for example, a saddle to a maximum, okay? In principle, it should be much easier than connecting to a saddle, and it is the case. And this gives us the idea that sometimes you actually have just the front, other times you will have a lot of oscillations there, and this can be viewed in this way in terms of dynamical systems. Okay, and this was all for the model, and we have done. So the question is, okay, for the model is fine, but do they exist in Euler? And the answer is yes. And perhaps I should stop here, right? Okay, so let me just thank you guys. For more reference, you can find them there.
Okay,
perfect.
Thanks a lot. We have time for maybe one or two questions before we go down to anything. So has there been anything you found that didn't also turn up in Euler? Are you quite happy with the kind of terms that you're keeping in these expansions?
The second study that we have done is actually looking at how well the model is doing against Euler, okay? So most of the times, the strongly nonlinear theory is working as it should, okay? Other times there are some discrepancies, okay? But this could be actually related to the question of, for example, when your intermediate layer is really thin, okay, does really the long wave approximation work or not? Okay, because I mean you have a very thin intermediate layer, right? So can you still say that or not? Especially if they have these kind of large bumps and things like that. Okay.
Yeah. Do you have to compare the length scales in two directions?
Yeah. So we have seen this that when the shallow water is violated assumption, you expect more discrepancies.
Yeah.
But overall, this is working.
Qualitative in terms of the zoo of solutions you
found. Oh yeah, there's no solutions you can. Yeah. And you put side by side what happens with Euler and the model. Yeah.
In terms of the density ratios, so how far can you push the model, and what are realistic values?
I mean, mathematically, you can do whatever you want with them, right? In the lab, typically people use. I mean, okay, if they want to model the ocean, typically they use salted water over fresh water, for example. And in that case, the density ratio could be 0.998, something like that. But for example, some people use, for example, silicone oil over water, for example. In that case, it lowers the density ratio to say 0.8 So some people have used 0.68, anything like that. Okay, so it really depends. But I mean, mathematically, you can do whatever you want. But you could describe air over water if you want.
Just wonder if there's any limitations in the asymptotics.
Yeah, we haven't. Yeah, I haven't looked at that in that extreme. No.
It was one of your small parameters there.
Yeah.
You had epsilon.
Yeah, I have another additional small parameter. I haven't done that. Yeah, I was trying to focus more on the side of experiments and the ocean, so it's always very small. So the next stage will be trying to see these things in the lab. I mean, in a very systematic way, right? That's what we want to do. In the first experiments by Miyata-Choi, she was not even aware of these solutions, so she never tried to find them. But that paper produced it in the Loughborough Institute of Hydrodynamics. They use a very different way of generating these waves, because they instead of starting with a 3-layer flow, they start with actually a 2-layer. And then what they do on the back of a gate, they have a different density, which is typically the average between the two. So they mix the thing, and then they lift the gate, and the thing goes immediately into the interface, and it's just whoosh, like an intrusion layer, something like that. And this is where they saw this thing. So it's good because it appears exactly on that region that we have. It is a small I mean, thin intermediate layer is where things are really happening, right?
And did they intend this, or is this an
No.
experiment? Yeah, so
No, it's cheaper for them.
Yeah.
That's how they do it. What's cheaper?
Excellent. So yeah, we'll go for discussions now and coffee, but thanks.
So one
Oh, yeah.
question about phase velocity, typical phase velocity in the ocean scale. So it goes like more or less square root of GH for the layer.
It's yeah, we have the reduced gravity there, right?
Yes. So do you know of any observations about arrival times? Because we talk about long time scale, right? What we've seen with tsunamis that might be comparable in terms of the arrival times we have very large tsunamis, but the compressibility actually plays a role in the.
These are much slower than the because it has the reduced gravity, right? So
Yes.
so the closer the two densities are or three densities are, the slowest the wave will be. Right?
Yes, but for that reason, maybe compressibility actually would have further effect because
Perhaps.
the travel time scale is much larger now.
Yeah. So what we see is that when we compare these models with, say, the real life, okay,
In experience or in the ocean?
in the ocean, I think so. These travel too fast, I believe. I think it's how it goes.
The model.
Yeah, the model. Yeah,
So this
they
is something-
overpredict the speed. Yeah.
Yes. So when we include compressibility, then we have an adjustment.
A tuning. Okay. Yeah. Yeah, I never worked with compressible flow. Maybe it will come now.
Excellent. Let's thank Ricardo again.
Thank you.